Acids and bases in a nutshell. So let's go over the basics of acids and bases and some of the mathematical things you need to be aware of, as well as some of the concepts. So first thing we're going to do is talk about acid and base theory. Now there's different theories. There's Lewis theory, there's Arrhenius theory, but the main one we're going to focus our attention on is Bronsted-Lowry. This is how we're going to identify our acids and bases. And the basic premise of this is that all you're focusing on is the movement of hydrogen. That's how you identify your acid and your base. Your acid is whatever substance donates a hydrogen. So if you look in the scenario, and you're not going to obviously have these arrows and everything telling you where everything is going, so you have to predict what's happening. And usually you'll get the reactants and the products, and your job is to look at it and say, okay, well, you're going from H2O to OH minus. So you lost a hydrogen. So that makes that the donator. So this is your acid. So H2O will be considered your acid in the situation because of loss of hydrogen. The way you recognize that, once again, you look at the left, you look at the right, and you see that the difference between these two is a single H. This lost an H. So that's the reason it's the acid. Same respect, the reason this is a base is because you have NH3 on the left, but you have NH4 on the right. So what happened? It gained a hydrogen. So it's accepting a hydrogen. It's a hydrogen acceptor, so that makes it a base. So that's how we identify ammonia as your base and H2O as your acid. On the other side, whatever your base changes into after getting this hydrogen is called your conjugate acid. So this goes into this, which makes it the conjugate acid. Ammonium is the conjugate acid, and then the acid switches into the conjugate base, which is hydroxide. So the thing the acid changes into on the product side is considered your conjugate base, and whatever your base changes into is considered your conjugate acid. That's the way the theory works. And if you want to look at it a different way, if this reaction was going to the left, then this would be considered your acid because it's losing an H to become an H3, and this one's becoming your base. This is your base because it's changing into H2 on the right side, or excuse me, on the left side. So easy way to do it is just look at the left versus right, and just the one that gained a hydrogen is your base, the one that lost hydrogen is your acid. Just keep it that simple. All right, the conjugate acid and base we just talked about, they're what the acid and base on the left side changes into. So in the case of HNO2, by losing an H, it becomes NO2 minus, and that's considered the conjugate base. So the acid has a conjugate base, the base has a conjugate acid. So that's another way of not brain farting this. I just realized they're opposite. The acid is a conjugate base, the base is a conjugate acid. And the way they happen is just by either gaining a hydrogen in the case of the base, which is H2O, or losing an H in the case of HNO2. That's how you identify your conjugate acid and your conjugate base, just by looking at the left versus right and understanding that you're losing an H to become the conjugate base and you're gaining an H to become a conjugate acid. All right, amphoteric. Any substance that could act as both an acid or a base is considered amphoteric. Easy way to identify these, if you don't want to memorize a whole bunch of them, is look for substances that have an H and a negative charge. Those are always amphoteric. The one exception is H2O. H2O is amphoteric, but it has no negative charge, it has no charge at all, but it is amphoteric. That's the only substance that's neutral and has the amphoteric abilities. Everything else basically has a negative charge and a hydrogen. So if you notice in each of these examples, you notice how they have an H and they have a negative charge. And the reason this works is because they could donate an H, which means that they can act as acids. And because they have a negative charge, they can accept an H, which means they can act as a base as well. What's the significance of amphoteric? They're just chemicals that could be acids and bases. That's pretty much the long and short of it. So you just need to be aware of their existence. So what happens when an acid dissolves in water? So you have HCl, and you're dissolving it in water. And what happens is that the acid will dissociate completely. So all this H and Cl will become H plus and Cl minus. For any strong acid, they dissociate completely. There is no compound to say anymore. It's just two ions. And in this situation, what happens is that the hydrogen, because it's an acid, goes into the H2O molecule, which is your base in the situation. And as a result of that, you form H3O plus, also known as hydronium. On the left side, you're left with just chloride, which is going to be spectating. So theoretically, if I was doing a net ionic for this, it'd be H plus H2O versus H3O plus. And the reason for that is because you do not write spectators. And chloride, which is not doing anything in this reaction except watching, it's called spectator. So acid loses hydrogen to water to make an H3O. Strong acids completely dissociate. So just remember strong acids, and you should hopefully memorize your strong acids, which I'll just write in here real quick, HCl. It's basically your halogens. If you just go down the line, you get most of them, HI, HBr, then you have HNO3, H2SO4, and not as popular, but still considered a strong acid, is HClO4, perchloric acid. Weak acids, on the other hand, dissociate very little. So out of 100 molecules, one of them breaks apart. The other 99 stay together. So like if you have acetic acid, which is CH3, COOH, 99 of them will look like this. One of them will do this thing. And that's what makes them a weak acid, because they don't dissociate much. So they don't produce hydrogen ions or hydronium, whatever you want to call them. And just to kind of discuss hydronium real quick, technically it's hydrogen ion, but anytime there's water present, the hydrogen is going to automatically attach itself to the water and produce hydronium. So hydronium and hydrogen are synonymous, but in nature you really find hydronium because you always have water in solution. So you don't really find H plus floating by itself. We write it that way sometimes to make it easier, but realistically it's hydronium that's really being produced. All right, here's some different acid strengths. So it depends on how strong the bond is with hydrogen. The stronger the bond with hydrogen, the weaker the acid. So strong bond, strong H bond equals weak acid, because it doesn't want to break apart. If you have a really strong attachment to hydrogen, you're not going to want to dissociate. If you can't dissociate, you're a weak acid. Simple as that. You have to completely dissociate to be considered a strong acid. Vice versa, the weaker the bond, the stronger the acid. So when we're identifying these strong acids on top, these are all substances that dissociate completely, which means you could assume that its bond with the H is very weak. And that's exactly what it is. It's very weak. So it's going to dissociate very easily. And you can see with the top 5 here are basically the 5 acids we mentioned earlier. Perchloric's not on this list, but it would be here next. And what you'll see is that they have very high K values. Remember, K indicates favoring products. So a very large K means you completely favor the products, like you have almost exclusively products. If you have a high enough K, you're actually going from an equilibrium scenario into a stoichiometric scenario, because there is no more reactants, it's all products. Equilibrium usually deals with Ks that are less than 1. There are some exceptions, of course, but when you have a K that's really, really large, like 10 to the 5th or 6th, it's not equilibrium anymore. It's favoring products. You could just assume that. The thing I want you to notice about these is that if it's a strong acid, its conjugate is weak. So if HI is a strong acid, that means the conjugate acid for this, or conjugate base, excuse me, which is going to be I minus, is a weak base. It's a flip-flop conceptually. And if you look down here, this particular chart doesn't do a good job giving you the comparison for all of them, but like something like HNO2, you see how its K is 10 to negative 4. That's a pretty weak acid, right? Because anytime your K is less than 1, you assume it's a weak acid, just FYI, or weak base, whatever. If it's acid or base, it's weak, whatever it is. So in this situation, because this K is small, you can assume the NO2 minus is a stronger base. So weak acids have stronger bases. Strong acids have weak conjugate bases. It's a flip-flop. So basically what I'm trying to tell you is if the acid is strong, then the conjugate is weak. If the base is strong, the conjugate's weak. And it kind of makes sense mathematically, because if you look at it this way, your K is this, right? But what if I want to figure out the K for the opposite direction? Be 1 over 4.6 times 10 to the negative 4, right? The reciprocal of your K gives you the inverse reaction. And that's going to be a very large number. So it makes sense that that other side is going to be strong if this side is weak. Here are your strong acids again, in case you didn't memorize them. The other thing you want to pay attention to, the more oxygens you have, the stronger the acid. The reason for that is that the oxygens pull electron density away from whatever is bonded to the H. And as a result, it weakens that bond with the H. So if you have a weak bond with the H, what do you have? Stronger acid. So where is this really applicable? Comparing, like, let's say H2SO4 versus H2SO3. This is a strong acid. This is a weak acid for H2SO3. The reason this is weak, that one less hydrogen. I know it's like one less hydrogen makes that big of a difference. Yeah, it does. Because that one less hydrogen means less electrons are being pulled away from the bond with the H. And as a result of that, you make a weaker acid. The more electrons you're being able to pull away, the stronger the acid's going to become. So more O's means stronger acid. So if you're comparing two compounds or two acids, and the only difference in the number of O's, the one that has the most O's wins. It's going to be the stronger acid, and that's always the case. Bases are just similar to strong acids. They dissociate completely, so that's the main feature you're going to be looking for, is dissociation ability. They basically match your solubility rules. So if you remember which hydroxides are soluble, you've also memorized your strong bases. The reason is that the more it's able to dissociate, the more soluble it is, the stronger the base. Remember, acid and base strength is based on dissociation. The more it dissociates, the stronger it is. So that's an easy way to look at it. So group 1, along with barium and calcium, are considered your strong bases. Everything else will be considered weak. All right, interpreting K for acids and bases. The larger the K, the stronger acid or base. We mentioned this earlier. If acid or base is large K, the conjugate is weak and vice versa. So this K is greater than 1. So we could assume that this, and we know this is a strong acid anyways, right? So this implies that this reaction favors the product side. Okay, wonderful. So if HBr is a strong acid, then its conjugate, which is this, will be weak. It's a weak base, right? Because remember, it's a conjugate base. Then if you compare that with different reaction, actually, let's mention one more thing about this. Because this is a strong acid, basically this is what you have. You have acid, base, conjugate base. You can assume that this is stronger acid than this, right? So if this acid is strong, then this means this one's weak. How do I know that? Because your K is greater than 1, it's favoring the product side. If this was a stronger acid in HBr, the reaction would favor the other direction because it wanted to dissociate. And that's not what's happening. We could also assume in this situation that this is a stronger base than bromide. The reason for that is that if we identified this as strong acid and this is a weak conjugate base, then that means this is a very weak base because it's a very strong acid, which makes ammonia a little bit stronger. So you could actually infer, based on this information, that your HBr is stronger than ammonium, and your ammonia is a stronger base than bromide. So you could get a lot of data just from a K value and being familiar with strong acids, obviously. All right, so here's example 2. You have carbonic acid. K is 1 times 5.61 times 10 to the negative 11. That's a very small K. So you could assume it's a very weak base. Since this is a very weak acid, and because it's a very weak acid, its conjugate is going to be a very strong base. And for those wondering, how the heck do you know that? Well, let's take a look. This would be what your dissociation would look like, right? This would be your K. So your K going this way is this, right? So what the K going this way would be? Well, if you remember from our discussions about calculating K, when you flip a reaction, it's the reciprocal. So it's 1 divided by 5.61 times 10 to the negative 11, which is a ridiculously small number. And I'll run that through the calculator right now just to verify that. Second E negative 11, give you 1 over X. 1 divided by 5.61, second E negative 11. You get 1.78 times 10 to the 10th. Look how large that K is. So that proves that this thing really wants to go this way, which means this thing really wants to dissociate. Or in this situation, it wants to accept the hydrogens. It's a strong base, right? Bases accept hydrogen, strong acids donate hydrogen. So in this situation, because you have such a large K going the other way, this thing really wants to accept the hydrogen. That makes it a very strong base. All right, so what is the strongest acid in this situation? Your K is less than 1. So that means that the reaction really favors going toward the reactants, not toward the products. If your K is greater than 1, you favor products. Your K is less than 1, you basically favor the reactants more. So that means that this thing is your acid. First thing we do is identify our acid or base. So let's get that out of the way. That's your acid. That means it's your base. And how do I tell that? You went from H2PO4 to H2PO4, lost a hydrogen, so that's your acid. And because this became this, is your conjugate base, conjugate acid. So because your K is less than 1, we can assume that HF is a stronger acid than H2PO4. Why? Because this is a weak acid, so we're going to assume the other acid involved is going to be stronger than it. And for the strongest base, you have, in this situation, H2PO4, and the reason it's H2PO4, because we already established that as being a strong base, right? Because we figured out your K is less than 1, and that's the direction we're going to go with it. All right, so moving on. Now let's get to equilibrium. So first off, strong acid and bases don't reach equilibrium because they have such large K values, so there is no equilibrium calculations. There's no chart for them. If you have a strong acid or a base, use stoic, get your numbers, called a day. You don't need to do anything cute. The problem is you usually don't have those. You have K and KB related questions, which are weak acids and bases. So first thing about K and KB, remember K is for weak acids, KB is for weak bases. The relationship between them you need to be aware of. So whenever you multiply K times KB, whatever number it is, you should always get to 1 times -14 as your K value. That's just the standard. So you need to remember that if I were trying to solve for Ka from KB, I use this calculation and vice versa. If I'm trying to solve for KB, I'll plug in my value for Kw, which is this, and divide it by my Ka. So this calculation basically allows you to go between K and KB. That's the long and short of it. If a question involves a weak acid, then you must use Ka. Likewise, a weak base requires Kb. So how do you recognize it? Here's a generic expression for Ka. You have HA produces H3O and A minus. And basically, this stems from this reaction. For those wondering where this came from, you have HA plus H2O produces H3O plus A minus. That's what this is. Just a generic, this is what usually happens. HA will be the actual acid, weak acid, and H3O will still be there, and A minus will be obviously the anion. But this is the way you want to remember it because it's generically always the same way. Generic expression for KB, on the other hand, HB plus OH are the product. So basically you have B plus H2O. Remember, since this is a base, it's going to accept a hydrogen. So that's where you get the HB plus. Why plus? Because B was neutral and you're adding a positive charge to it. So that's why it became HB plus. And you have OH minus as your other byproduct. So that's where this stems from. And B will be like a base. I mean, for example, be like an H3 plus H2O produces NH4 plus OH minus. So that's what it looks like realistically, right? Why do we want to remember it this way? Because it's easier to keep track of generalities that way. So basically, OH is in the product. You have a KB question, H3 on the product, you have K. Really easy way to figure it out. So anytime you have H3O or H plus, because sometimes you see H plus instead, depending on how you set it up. Like if I did this reaction without H2O, which you'll see in some resources, they'll do this. So it'll be H plus over H plus times A minus over HA. Same exact thing as this. H plus and H3O are the same thing. So don't get thrown off by that. But either way, it's the same concept. So whenever you have H3 or H plus, it's going to be K. Whenever you have OH minus, it's going to be KB. Always, without fail. So here's an example. Weak acid reaction with water. You have HA plus H2O produces H3O plus A minus. And that's what the reaction looks like. Generic. Obviously, we don't have the actual chemicals. But even if we did, same setup. Things you need to be aware of. Larger K means more dissociation, stronger the acid. H3O is the same thing as H plus, which we mentioned earlier. So don't get confused by that. In calculation, we can assume H3O and A minus are equal at equilibrium. Why is that? Because at equilibrium, you can use stoic between products. So if I give you H3O, and typically what happens, when you start a reaction, you typically don't have H3O or A minus in the beginning, right? So these are 0. So that's why, you can make a generic thing, this is equal, but just remember it's only equilibrium because there are what's called common ion questions where you're given one of these as well. So it's not you can't assume if I have H3O initially that A minus is the same initially. This stoic never works initially for two chemicals. I want to make that very clear. Stoic for equilibrium questions only work at equilibrium. So that means once the reaction is stabilized, now you can use stoic. Before that, you can't. You cannot do it for initial concentration ever. That's never an option. So don't ever make that mistake that, oh, I have H3O initially, so A minus is going to be the same. No, it's not. Don't do that. Don't make that assumption. It's never going to be the case. Same with the reactants. They're not going to be equal to each other initially. They can be if they give you those numbers, but you can't assume them to be. All right, so type of chemical equations possible. Type 1 for acid and bases when K and Kb are given. This is your generic approach. So either you're giving a KB question or a Ka question. So these are your only two choices when you have a question that gives you just an acid or a base. There's no buffering, there's no neutralization, nothing cute going on. They just say, okay, you have this acid initially, what's the pH, what's the K, whatever it is. When there's no reaction outside of, just a simple reaction with H2O, this is what you use. So this is not the most common, that's the easiest, but it's not the most common. 2, when an acid or base is added to a weak acid buffer. So this is a situation, a buffer is when you have a weak acid as conjugate, and we'll talk about this in a little bit. I just want you to be aware of these are the possible scenarios, because like with thermal and other constants we've talked about, if you know what your options are to begin with, you narrow down your angle of attack, and that's what you're trying to do in these questions, is not get confused by, okay, which way do I go with this? These are the only possibilities for acid-base questions. The ones I'm going to show you right now, the 4, that's it. These are all the possibilities. So it's one of these reactions every time. So the hardest thing is going to be figuring out which one it is. So if you're adding H3O, the H3O reacts with what's considered your conjugate base. This will make more sense when we get into buffers. For now, just realize this is one of the reaction types. And this is if you add the base. So a buffer is basically a weak acid in its conjugate or a weak base in its conjugate. So for this, the weak acid is HA, so its conjugate is going to be A minus. How do I know that? You just take an HOA. That's what the conjugate base for any acid is, one less hydrogen, right? So this is a buffer. What a buffer does, it resists changes in pH. So if I had H3O or OH minus, acid or bases, the job of a buffer is to prevent the pH from changing, so it consumes those. So the way it does it, the conjugate base reacts with any acid you add, and the conjugate acid, or excuse me, the acid, not the conjugate acid, just the acid reacts with whatever base you're adding. And this is the reaction possibilities. So how do you know to use this? Because they give you a buffer scenario and they're adding an acid or base. You notice these does not have any acid or base being added. When they add acid or base, this is one of your more likely options. So this is for a weak base. Same concept, so all I did was take my base and its conjugate, and then I reacted accordingly. If it's the base, it reacts with the hydronium you're adding. If it's the conjugate acid, it's reacting with any hydroxide you're adding. This will make more sense when we talk about buffers in more detail a little later. For now, just realize that if you have a buffer scenario, and you'll know you have a buffer scenario, that these are the only possible reactions. Either it's going to be 2 or 3. If it's not a buffer, then you look at 1. That's the way you want to start thinking. And that's what makes this a little bit easier if you think of it that way. Neutralization involving strong acid and bases, it looks like that. Very uncommon. You're not going to see it very often, if at all, but just be aware that's what it looks like. Notice you don't have any ions, any spectator ions involved. So the cation that attached to the hydroxide is gone. The anion attached to hydronium is gone because those are all spectators. Strong acid and bases always looks like this reaction. Just going to be OH plus H3O, and then H2O is your product every time. You name the strong acid or base, this is what it looks like. So those are the only possibilities. You have 4 types. This one's unlikely. So realistically, these are your 3 types. What's the most difficult ones? Obviously these down here, right? Because they're going to involve much more thinking. The top is when there's nothing cute going on. You're not adding an acid or a base, so it makes it a little bit easier. The bottom one's when you are. All right, so question, calculate the hydronium of a 0.3 molar acetic acid solution. Notice They're not adding an acid or a base to this. It's just the straight acetic acid. And all I want to know is what's the hydronium concentration. Okay, that's going to be at equilibrium. That seems pretty simple. So which type is it going to be? Type 1. How do I know it's type 1? Because there's no hydroxy or hydronium being added in addition to. You have only one chemical and one concentration, right? Makes it a little bit easier. If you have two different concentration of chemicals, then there's a good chance it's a buffering type question. So all I do is plug and chug. There's my 0.3. There's a 0, 0, because I don't have anything for them. There's my x's, just like you would ordinarily do. The beautiful thing about acid and base questions, it's always going to be x. There's no 2x, 3x, 4x, none of that, because all the coefficients are always going to be 1. So at least you can take that out of the equation. You can't screw up by miswriting the x's or miswriting the exponents, because they're always going to be 1s. That makes it a little bit easier. Here's your equilibrium. I just brought these down. Now the math. So remember, first thing you do is write your expression without the numbers. Now you plug in your numbers. So what can I do at this point? Can I assume x is small? I can't do perfect square, right? So I'm going to go with x is small, because if you look at this, this is 3 times 10 to negative 11. This is negative 5. This is 3 or more apart, so I can assume x is small. That's what I'm going to do. So I'm going to assume x is small. X squared is equal to, I just distribute the 0.3 to both sides and gets rid of it on the left, puts it on the right, do the math. X equals 2.3 times 10 to negative 4, and that is our concentration of hydronium. And I'm done. So that's how easy it is. All you have to do is just plug and chug, and because you knew it was a type 1 question, because you knew this was a assumed question, which is a type 4, you can get away with this really fast. That's why it's so important to think in terms of that. What is my type available? pH is defined as the negative log hydronium concentration. So to calculate the pH, you just take the negative log of what the hydronium is. So for that previous example, if I take the negative log of 2.3 times 10 to negative 3, which is like probably what, 2.8, 2.7, something around there, that's how you get the pH. You just take the negative log of that. That's all it is. If you get a 7, it's neutral. If it's less than 7, it's acidic. If it's greater than 7, it's basic. Those are your 3 options. There's nothing else going on. Calculating POH, similar to pH, except POH is negative log hydroxide's concentration. Which one do you use when? If I have hydronium, I calculate pH. If I have hydroxide, I forget POH. And then I would use this to go to pH. They're going to ask you for pH 99.9% of the time. So if they give me hydroxide, I would use this, get a number, subtract from 14, and get my pH. Because pH plus pOH equals a 14. So if I have one of these, I can figure out the other one. So let's say the pOH was 6. So 14 minus 6 gives me a pH of 8. That's how you do it. So if your pOH was 6, and you calculate it, do the math, right? So it'd be just 14 minus 6 is equal to 8. That's equal to your pH. Because you're solving for this. You have 2 of the 3 variables. You have this, and you have this, and you just do the math. So you're just trying to avoid having to go between hydronium and hydroxide, which, by the way, in case you didn't know, when you multiply the hydronium times the hydroxide, it is equal to 1 times negative 14. Remember the Kw calculation, the Ka times Kb equals 1 to the negative 14. So does hydronium times hydroxide. So that's how you do it. So that's how you do the math for it, if you're interested in doing it that way, which is a lot easier. So basically you have 2 choices. Either you could do it this way. I could get my OH, solve for H3O. So that would mean I would do this thing. So if I want to figure out the H3O concentration, I'll do 1 times 10 to negative 14 divided by OH. I'll get a number, then plug it into this to get my pH, or I could just figure out the pOH, subtract from 14. What's the better option? Well, which one do you think you're going to make less mathematical errors? I'd go with doing the pOH first. All right, to calculate for any of the following that is given, H plus, OH minus, pH, pOH using the following data. So here's my H3O, here's my OH minus. So to get my pH, just negative log of that, which is 3.64. For POH, it's just going to be negative log of 4.3 times negative 11, which is about 10.36. And that's all I'm going to say about that. Indicators and pHs. So how do we determine the pH of a substance? So there's two different tools. You have a pH meter or you have an indicator. Indicator is a substance that changes pH in a very specific range. So for this particular methyl violet, it changes color somewhere between 0 and 2. So it'll go from yellow to purple to indicate you've gone from 0 to closer to 2. So if you're a violet color, whatever this looks like, then you assume you're close to 2. That's a range. That's not really great detail, right? Same thing with this. If I'm using the most common, most popular one is phenolphthalein, which is colorless and then turns pink. Most labs use phenolphthalein because neutralization is around 7. You can see this is beyond 7 because in order to do 7, you want to have an indicator that's between this line, right? But as you can see, phenolphthalein, the most popular, is usually between 8 and 10 as its range. Okay, why is that significant? So this is what the assumption is. Usually you're going to do a weak acid with a strong base. Your pH should be above 7 in neutralization. Neutralization is when the amount of acid and base are equal to each other, such that now your solution is what's referred to as the equivalence point. And we'll talk about that in more detail in a minute as well. But for now, let's assume that you're trying to figure out for what phenolphthalein. What phenolphthalein will do, when you get to around 8, it'll change from clear to pink. As soon as it does that, you typically stop the experiment, you collect your data, and then you do the math that's related to it. But you notice that this is not very exact, right? Because what if it's like a little darker shade of pink? What if it's super pink? Well, if it's super pink, you screwed up. Why do we do this at all? Because not everybody has a pH meter that calculates data every second. So you need something to do neutralization labs in high school. So typically you use an indicator because it's not super accurate, but it gives you at least a ballpark figure. Like if in the case of this thing, it gives me a range of the pH of neutralization, but it's not an exact number. It's somewhere between 8 and 10. That's pretty broad. A difference of 2 pH points. So that's why, it's not ideal, but it's an option. pH meter is by far the most accurate. And indicator gets a range, and that's why it's not ideal. But like I said, if you don't have a pH meter to collect data every second, then you have no choice but to use an indicator. You need something to tell you the reaction is done. And this is about the only thing that can do it. All right, calculating Ka from the pH. The pH of a 0.1 molar solution of formic acid at 25 degrees, 2.38. Calculate the Ka for formic acid at this temperature. Okay, this has got a lot going on. You have a single acid. So it looks like it's a type 1 question, right? Because you just have a concentration for, you're not adding. It didn't say you're adding a base to this acid and neutralizing it. So right now we're thinking type 1. It's a Ka question because it is a weak acid. And also they're asking for Ka. Now, could they give you a weak acid and look for Kb? Of course they can. You got to pay attention that doesn't happen. So what do I do with all this data? First off, I have initial concentration. Beautiful. But remember, in order to solve for K, which is a type 1 question, right? For equilibrium type calculations, I need to have all concentration of chemicals. I've only have one. How does this make any sense? Here's how. You have this, the pH. If you take 10 to the negative 2.38, so take 10 to the negative pH of the value, you'll get your hydronium concentration. So you know how you do negative log of this to get to the pH? You can go the other way too. If I have the pH, I go 10 to the negative of the pH, and it will give me my hydronium concentration. And if you have hydronium, and by the way, the pH is based on equilibrium always. So if I have the equilibrium concentration of hydronium, guess what else I have? The other product. So now I have the equilibrium concentration of both products and basically the equilibrium concentration of the reactant too, because it's going to be 0.1 minus this number. So when they give you pH, they're actually giving you equilibrium concentration of the products, which is very useful. All right, so we know we can find H3O, which is the same as a CaOH minus from the pH. So notice how I rearranged it. There's my number. So that's concentration of H3O, and it's the concentration of the anion as well, CaOH minus. plug and chug, 0.1. I'm going to plug in the numbers instead of x's because I actually have values for this. Because I have these, right? That's what x is equal to. So I just plugged it in everywhere. So here's my three numbers. Remember, to solve for k, which is a type 1 question, you need everything equilibrium-wise. And you have everything now. So now you got to do is plug and chug into your k expression. There's your products over reactants. And your k comes out to be 1.8 times negative 4. Pretty small number. So it's a weak acid, and it looks like a weak acid. So it seems like a valid number. All right, the other concept you need to be aware of besides the involvement of pH and how to utilize it, which you just saw, is percent ionization questions. They're used to determine how much an ion actually dissociates. So percent ionization is equal to H3O over initial times 100. You could basically say X over initial times 100. I put it as H3O because, that's just one of the two products that you'll usually have. But you could do it. It's basically X over initial. Because if you have a base question, you don't have H3O, right? You have OH minus. So maybe an easier way of looking at this equation would be just is equal to X over initial. And X just basically represents the concentration of the two products, right? So if you just plug in one of the concentration of the two products, divide by initial concentration times 100, you get percent ionization. So here's my values. Here's the concentration, the equilibrium of 4.2 times negative 3. All I gotta do is just plug and chug. 4.2%. So what does this mean in simple English? This is how much it breaks apart. This proves it's a weak acid. Only 4% of the weak acid associated. So yeah, that's very weak. They'll ask you this question typically, and they'll ask percent ionization or percent dissociation. They're kind of synonymous. And all you have to do is just take your X value at equilibrium. You have to make a chart, obviously. Divide by your initial times 100. You're done. That's all you got to do. Polyprotic acids and pH. So this is not really tested on the exam, but I just want you to be aware of what they are. Polyprotic just means multiple hydrogens. So instead of having one hydrogen in the acid, you have multiple. So these are all examples of polyprotic. You should realize or recognize sulfuric acid, which is a very strong acid. Look at the K. These have multiple dissociations. You don't need to really worry about that. They're not going to ask you based on K, K2, K3. They don't do that kind of stuff. But just be aware they exist. The other thing you want to note is that the K does decrease as you go. The first dissociation is going to be always higher than the second and third. The reason that's important is when they're asking for concentration of chemicals at each point, and we'll talk about that in a minute. But for now, just realize that each time you are losing a hydrogen, it becomes harder to lose the next hydrogen. That's why the Ka becomes smaller and smaller as you go. All right, so this is the way they'll test you on it. Which of the chemicals above has the highest concentration? So if you notice, this has the highest K out of all the three of them, right? So the most dissociation is going to occur at the first point. So what are you producing a lot of? You're producing a lot of hydronium, right? And you're also producing some of this. But this K still indicates that you have more reactant than product, right? Because it's products over reactants gives you this number. And if this number is less than 1, that means this number is bigger than the two products, right? That's how the math works. So based on this, you can assume that H3PO4 is probably going to be the substance present there in the highest concentration. So what's going to be number 1? H3PO4. How do I know this? It's a very small K, so that means the reactant is going to be the highest value. For those wondering, well, what about this, H2PO4? Look at how small the K is. Only small amounts of this being produced each time. Because it's a weak acid, you could usually assume that whatever that weak acid identity is, that's going to be the highest concentration because it's going to stick together predominantly, right? Only like 4% is going to break apart. The rest is going to stick together. This is going to be present in the highest concentration. What's number 2, do you ask? Well, H2PO4. And for those wondering, well, how do I know this? Because of the highest K value. So the most dissociation is going to occur at this first step. You can make an argument for H plus too. It's going to be the same value as this. But they'll typically give this as an option, not this, because this is too easy. You could see this is going to be number 2 for sure, right? Because it's being produced repeatedly. Whereas this chemical, they're all different. So that's why they're not going to make it that easy. They're going to compare this, this, and this against each other. So what's going to be present in the lowest concentration, you ask? Well, lowest is going to be PO4, 3 minus. Why? Look at how small that number is. Very little is being produced. So what's in between these two? The other chemical. So that's how the hierarchy goes. So the weak acid has the highest concentration, then whatever it dissociates into, because it has the highest K value, which is H2PO4. Then what's next on the list is HPO4, and that's because it's the next Ka value. So you can just basically go in the order of K. That's how they're going to test you on polyprotics, is making sure you understand how these can be used to determine this. So the one that has the lowest concentration, as we said, was going to be phosphate. All right, 0.5 molar solution of ammonia has a pH of 11.48. What's the Kb of ammonia? Note pH and pOH are based on the equilibrium concentration of hydrogen and hydroxide. So you have initial ammonia, you have pH, so beautiful, I have equilibrium concentration of both products, and looking for Kb. Oh, I'm good to go. Now, the only problem here is that because it's pH, this gives us H plus, right? We don't want H plus. It's a Kb question. What does Kb imply? OH minus. So what do I want to do from the get-go? Change this into POH and go 10 to negative of that to get hydroxide. That's the better play. Because look at your reaction. You have you don't have hydronium on the product side. What are you doing with the calculation? If you do 10 to negative 11.48, you get hydronium, but there's no hydronium in this reaction. So it'd be a bad first move. So I'm going to get my POH first, 2.52. Go 10 to negative that, give my hydroxide, which means I have equal equilibrium concentration of both hydroxide and ammonium, which is what I want. Plug it into the setup. So I'm going to put X's in the beginning. But of course, we know the values, so we could do substitution really quickly. So this is going to equal to this. This is going to be 0.5 minus this, which is 0.497. So when I do my chart with all these numbers plugged and checked correctly, notice these two are equal to each other as we expected because we had the pH, excuse me, POH. And here's the equilibrium concentration of this. So now we can solve a K. Type 1 question, right? So you get 1.8 times 10 to negative 5. And that's it. That's all you got to do. So once they ask you for K, once again, your mind should be like, okay, it's a type 1 question. You're looking for K. Type 1, once again, is when you're looking for K. Type 2 is when you have a perfect square. Type 3 is quadratic. Type 4 is going to be assuming X is small. Once you figured out they're looking for K, once they ask you that question, you're like, it's type 1 question. I need to have all my equilibrium concentrations. And you go from there, and you're going to avoid making silly mistakes. Salts. When an acid and a base react, the byproduct of it is called a salt. So, for example, when HCl reacts with NaOH, the salt is NaCl. So the salt is basically the two spectator ions that are left over, what compound they can make. That's what it is. When the reaction is strong acid plus strong base, the salt is going to be neutral. Kind of makes sense, right? If they have equal strength going in, then of course whatever they produce is going to be neutral because they're going to bounce each other out. When the reaction is a weak acid plus strong base, you get a basic solution. So if the base is stronger, your solution, your salt is going to be basic. If your acid is stronger, then your salt is going to be acidic. So it's really simple logic when you think about it. If the base is stronger, you're going to be basic. If the acid is stronger, you're going to be acidic as far as the salt. That's how you determine it. All right, common ion effect questions where you have the concentration of a reactant in one of the products. So this is the little twisty questions. Notice once again, this is a type 1 question for acid and base equilibria. There's no hydronium or hydroxide being added to a buffer. We're not there yet. So what you're basically going to be doing for these is that they're going to give you the concentration of an ionic compound, which will always be basically what you have on the product side. That's the way this always works. So when they give you an ionic compound, ignore the compound as a whole, dissociate and ask yourself, which one of these ions looks like the reaction I just wrote? If in the case of strong acids, they get a little cuter, or strong base, they get a little cuter with this, they'll give you like HCl. And you're supposed to know, oh, HCl is hydronium because it completely dissociates. Or they give you, whatever the strong acids are, there's 6 of them. They'll give you one of them and give you a concentration for it and say, okay, you have this concentration and you have this. So they'll give you this, and then you're supposed to do the math from there. the key thing to remember on this is that whatever they're giving you, it's always on the product side. Just look on the right side. If they give you some random chemical, look at it carefully. It probably shares characteristics of one of those two products. That's where you're going to add it. So let's see how this works. Calculate pH of a solution made up of 0.2 molar HF and 0.1 molar NaF. So they gave me K, so I'm not looking for K. So now the question is going to be a perfect square question, or it's going to be assumption question. We don't know yet. Now, as far as that's for equilibrium, now for acid base, what concept is this? What reactionary, right? It's going to be type 1. Why is it type 1? Because you have HF plus H2O. How do I know that? Because all they gave you is this, and they didn't give you anything. They didn't give you a buffer scenario to play with. Technically, HF and F minus can be buffers, but this is not going to play out that way. So what do? Write my expression, H3O, F minus, HF. And here's my numbers. Notice, for the first time in a long time, you have a concentration for a product. And you notice they're not equal. You can't assume they're going to have the same initial concentration, right? So minus X plus X plus X, 0.2 minus X, just bring it down, 0.1 plus X, and X. So what is X equal to? Well, we're looking for pH. That's the whole point of this. So we're going to solve for X because we want hydronium. So right into the expression. Now, can I assume X is small? Well, this is 2 times 10 to negative 1 versus negative 4. It's 3 or more apart. So we can assume X is small. The one thing people will screw up with, they forget that you're supposed to assume any addition or subtraction is going to be small. So both of these go away. Most commonly, students would just get rid of the bottom one and keep the top one. Don't do that. If you're assuming subtracting X is small, you have to assume this adding X is small as well. So there's my new numbers. Plug and chug. And you end up with this. So pH is equal to negative log of 1.4 times 10 to negative 3, which means 2.85. And you're done. That's all you got to do. Once you solve for X, you have hydronium, and then just plug it into negative log formula, and you have your answer. So that's how you deal with common ion questions. And the way you recognize it, because they'll give you initial, and they'll give you a ionic compound or an acid, and have you predict what's going on. All right, calculate the concentration of acetate for a solution that contains 0.1 molar acetic acid, 0.05 molar HCl. Okay, so once again, we have two concentrations. So it's a common ion question. We have K, so it's going to be either type 2 or 4. Now, as far as the math's concerned, HCl is basically hydronium. So that's where you plug it in. And this goes over here. And now all we have to do is do our minus X plus X's. Remember, this is the 0 side, so that's why it's plus X on this side, minus X on this side, because you can't get a negative number. You can't do minus X on the 0 side ever. Write my expression, plug and chug. So am I going to assume? Looks like it, because it's not perfect square. If it's not perfect square, you could probably 99% of the time assume it's an assumption question, unless they're really being nasty and give you quadratic. You still verify, obviously. You look at the exponents, and these are 3 or more parts you could assume. So I'm going to assume both X's are small. Rewrite the equation without the minus and plus X. Solve for X, which is the concentration of acetate. And that's all you're looking for. And if I want to figure out the pH, I could technically, but not what they're looking for in this question. All right, so now let's get to the hard stuff, buffers. Combination of a weak acid and its conjugate or a weak base and its conjugate. Basically what it does, it prevents fluctuations in pH. The whole point of a buffer is to act like a sponge. You add acid, it eats it up. It adds a base, you eat it up. The whole point of a buffer is to make sure the pH is stable throughout an experiment or scenario. Buffer is able to maintain pH plus or minus 1, the original pH of the solution, until it gets all consumed. So buffers have a range of effectiveness. You can calculate that based on this Ka value. We'll talk about that. It's plus or minus that range. That's all I could do is maintain that kind of range. The more moles of buffer, the greater the capacity. The only time the quantity of buffer is important is how long the buffer lasts. The more components or amount of buffer components you have, the longer that buffer will be in effect. So here's some basics. Ideally, you need equal moles of components. So you want an equal concentration of the acid and its conjugate and the base and its conjugate. That's the best case buffer. When you have equal amounts of the two, the bigger the number, the better. To pick the best buffer, choose one with a pK close to the pH you're trying to maintain. We'll see what that looks like in a minute. Henderson-Hasselbalch. Used to calculate the pH of a solution when you have molarity of acid and its conjugate or base and its conjugate. This is going to be a shortcut you're going to be needing for buffer question. That's why I'm throwing it in here. It saves you a lot of time. All you need is a concentration of the acid and its conjugate or the base and its conjugate to do this calculation. This is basically proximal reactants. To solve, so if I'm trying to figure the pH of a buffer scenario, which typically what they do, they'll give you the Ka, and you'll be able to get these numbers somehow, or these, plug and chug and solve for it. This will save you an inordinate amount of time. So make sure you're comfortable using this, and we'll be practicing it, obviously. All right, so what's the pH of a buffer? That's 0.12 molar lactic acid, which is this thing, 0.1 molar in sodium lactate at equilibrium. So they give me equilibrium concentrations. Henderson-Hasselbalch is based on equilibrium concentration. They're giving it to me. So I don't need to do a chart or anything cute for this. I already have the end values. And I have Ka, which I'm going to use for the pKa. So watch what I do. I'm going to write the reaction for fun. Here's my setup. Just plug and chug. You have 0.1 molar for sodium lactate. You have 0.12 for lactic acid. Plug into the equation. You get 3.85 minus. So the result of this is this thing. So you could see when the top number is smaller than the bottom number, you're subtracting. When it's bigger, you're adding. It's a little mental shortcut to help you avoid brain farts and to kind of predict what's going to happen. Like if I know I have more product, then I know that my pH is going to go up. If I have more reactant, then I know my pH is going to go down. And that's what happens here. The pH goes down to 3.77. All right, so calculate the pH at which of the following buffers is the most effective. So remember I always said the buffer works plus or minus 1, its most effective range. So how do you determine that range? Really easy. Take the negative log of that number. That's your range. So for the first one, all you have to do is just, you assume that the concentration of these two are equal, because remember, a buffer is the most effective when they're 1-to-1 ratio. So I'm using the Henderson-Hasselbalch to show you how the math works, but realistically, all you need to do is just get the pKa. Just take the negative log of the Ka, and there's your number. That number represents where the buffer's midpoint is for effectiveness. So the range is going to be plus or minus 1 of this number. So minus 1 is going to be 3.2, plus 1 is going to be 5.2. So this buffer is most effective between 3.2 and 5.2. So they ask you a question, which one of these buffers is best if you want to maintain a pH of 5? You would pick this. Which one's the best if you want to maintain a pH of 3.6? This. What if you want to maintain a pH of 12? Not this. Because it's not going to work, right? It only works between 3.2 and 5.2. That's where the theory comes in. So when you get the pKa, what you're really doing for that buffer is identifying its most effective range. And then from there, you could ask whatever question they're answering, or answer whatever question they're asking you. All right, for the second scenario, my POH is 3.4. So if they're giving you hydroxide data, if they give you KB, you have to get the POH, not the pH first. I do want to point that out. They'll get cute with these questions. They'll give you that kind of question where they give you KB. They say, okay, what's the most effective pH range for this? And most students will sit there and write, 9.6 to 2.4 to 4.4, because they'll just calculate based on this number without realizing, oh, this is KB. That's going to give me the POH, not the pH. So the POH for this is going to be 3.4. So the pH is this. So the most effective range between 9.6 and 11.6. That's the most effective range for this buffer. And it makes sense. It's a basic buffer. You don't expect it to work in an acidic region. That's only you could have caught yourself. But in the event you think there's a possibility you're going to brain fart this, remember, this is only for pH. KB is only for POH. Make that correlation so you don't brain fart it. All right, determine which of the following buffers would be most effective in maintaining a pH of 6. So this is more complicated. So you can kind of eyeball these and realize this is going to be around 4 point something. This is about 8 point something, 4 point something. Well, these are actually KBs. I should correct myself. So this is going to be 4 point something minus 14, 8 point something minus 14, because you want the pH range. You don't want the pOH range. This is going to be exactly somewhere between 4.5, 4.6, something like that. This is going to be about between 3 and 4. The way I figured this out, by the way, for those wondering, like, how the heck do you figure this out? The shortcut for log is, look at the exponent. Your negative log of a number is going to be between that exponent and the number before it. So between 4 and 5, somewhere in that range. If I'm taking the log of this, my answer is going to be somewhere between 8 and 9. If you're taking the negative log of this, it's going to be somewhere between 4 and 5. Negative log of this is going to be between 3 and 4. All you have to do is use this as the endpoint, and the number below it is the lower endpoint, and that's the range. That's the number you'll get. Like if you do a negative log of this, these are the numbers you'll come up with. Like you punch in your calculator right now for 1.8 to the -5, you'll get something between 4 and 5, guaranteed. It'd be like 4.8, I think, or something. But this is an easy way to kind of shortcut log calculations. So to determine if we're going to solve for pKa for each, so for ammonia, 5.56 times 10 to the -10. So the pKa is equal to 9.25. So what I did here, I did it the hard way just to show you how it looked. I solved for Ka first because remember, Kb is equal to 1 times 10 to the -14 divided by your Ka. So that's where this came from, in case you're wondering. I wouldn't suggest doing it that way. I would have actually, realistically, just done a negative log of this, subtract 4. You can come up with the same answer. I just think there's a higher chance you brain fart exponential calculation, you will single-digit calculations. So anyways, your pKa for this is about 9.25. So it ranges between 8 and 10. All right, for the second one, for pyridine, same thing, did the more complicated way. You get 5.23, so the range between 4 and 6. You can kind of see that's the answer already, right? Because you want around 6. But we're going to have to calculate for that one just to make sure. So we're going to do that. So acetic acid, it's going to be about 4.74. You don't have to do the divide by because you just do negative log to get the pKa, right? These are Ka values. So it's between 3.74 and 5.74. And citric acid, 3.13, excuse me, so it's between 2.13 and 4.13. So based on calculation, pyridine would be the best buffer to use because it's effective in the 6 pH range. That's how you figure it out. You could eyeball it, and kind of get the numbers without doing all this crazy math. Like before I even started, I would have probably gravitated to a pyridine anyways, because if this was your POH, then your pH, right? Because this is going to be between 8 and 9. So your POH will be between 5 and 6, something in that zip code. So I could kind of eyeballed it and got the answer without doing all the extra math, but that's how you do the math in case you're wondering. All right, determine what the appropriate chemical pair is to make a buffer. So to do a buffer, all you have to do for this is a weak acid because the H in the beginning, right? If it has H in the beginning, it's a weak acid. So the conjugate is just going to be 1 less H, CN minus. If I have HCO3, what's going to be the acid for it? If that's the base, we'll just add 1 more H. So to go from here to here, subtract an H. To go from here to here, add an H. Real simple. Let's take H2CO3. Well, H3PO4 will be the best conjugate base for it, H2PO4 minus. What about for this one? What's the best, if that's the base, what's the best conjugate acid to make the buffer? Add an H. So you could see the buffer is really composed of a weak acid and its conjugate or a weak base and its conjugate. What about for this one? Well, an H3, just get rid of the chloride because you don't need it. CO3 minus, add an H, HCO3 minus, H2PO4, subtract an H, HPO4 2 minus. Now, if you go on to titration, the next concept that we're going to discuss is basically the way to determine the concentration of an unknown chemical. And the idea basically is that you have typically a clear solution, and what you're trying to do is figure out the identity, or the concentration of it, the Ka, the molar mass. There's a whole bunch of stuff you could do with titration, but it's for a clear solution. The reason I stress this is because we have another method we've discussed before for determining the concentration of an unknown, and that's spectrophotometry. For spectrophotometry, you need a colored solution. So if you have a colored solution, use that. If you don't have a colored solution, use this. This is primarily used for acid and base, but it can also be used for redox as well. So it's not just limited to only acid-base titration. That's the one we're going to go over predominantly right now. So the idea here is that you have an unknown chemical in here. So we don't know the volume. Excuse me, we do know the volume. We don't know the concentration of it, but the volume is known. Here we have the concentration is known. And we know the volume we're going to be adding because we're in charge of adding the chemical. So we're going to keep on adding it until you get to what's called a neutralization point. Now, the pH meter can help guide you into that, or you could use an indicator. It's pretty much up to you. The standardized solution is just basically means that the chemical you know the concentration of. So whatever you put in the burette, it's called standardized solution, which is just saying that you know the concentration that you put in there. That's all it is. So whenever you have the concentration and you have the volume that you added, you can get the moles of what you added. If I get the moles of what I add, I could theoretically figure out how many moles I have in here, and this is the way it works. At the equivalence point, the moles of this chemical is equal to the moles of this chemical. So if I can get the moles of this by multiplying the concentration times the volume, it is equal to the moles of this. If I have the moles of this substance and I have the volume, which you already gave you because you put the solution yourself, or they gave it to you, but you could measure the volume, then you can figure out the concentration, because concentration is nothing more than moles over volume. So that's where the concept of this comes into. Now, before we get into titration and full-blown angles, we need to first understand how to read a burette. So I just want to stress this. Burette basically measures the volume going downwards, because that's how you're adding the volume, the solution's volume. So in this particular situation, it says 22.2, but I mean, it's really hard to see it's 0.2. It's a little bit below the 2 mark, which is right here. But it's so little that, you have to kind of guess that. Nonetheless, you are supposed to guess whenever possible. That one's really hard. Here's an easier one. Okay, so you see how this one, there's 30, 31, 32, and we're at 33. So that's, sorry, 3 point. Sorry, it's 3.1, 3.2, and 3.3. That's exactly the 3.3 mark. So that's why we get 3.3 for this one. For this one, 3.1, 2, 3, 4, 5, 6, 7, 8, 9, which is right there. So what's the volume that I added? Because that's what you're really interested in. It's going to be 3.90 minus 3.30, which means I added 0.60 milliliters of solution. That's the actual volume that you're going to be working with, the 0.60. So just be aware of that. When you're doing these volume measurements before and after, what you're looking for is the change in volume, not the individuals. All right, for this one, same concept. Looks like it's 0. This is 1. So these are all 0.1s. So 0.1, 2, 3, 4, 5, 6, 7. But it's not exactly 0.7, right? It's a little bit below it. So maybe 0.74. You kind of guessed that last digit, and that's okay. That's okay. That's normal. For this one, that's initial volume. For this one, we have 49.123. And it's before the 0.4 line, right? So maybe 3.5. So what's the volume I actually added? 49.35 minus 0.74. That's the actual volume that you add, and that's the one you're interested in. So just be aware of that. want to measure the volumes is that what you're going to do is you can keep on adding until you reach what's called the equivalence point. Now, when you're doing with a pH meter, it's really going to be really easy to pick up on because you have exact number. But sometimes you use an indicator. And what the problem with the indicator is that it's going to overshoot your equivalence point almost every time. And what we call this color change, the point it changes color, is actually called the endpoint. Endpoint is different than the equivalence point. Endpoint is when your indicator changes color permanently. Because what ends up happening as you add your base or acid to the solution, it'll change color to yellow for a second, go back, change it, go back, change it, go back. When it stays permanently yellow, that's when you reach your endpoint. That's point one. In this particular situation, your pH will be somewhere between where this change occurred. But because you don't have a pH meter in this experiment, you're going to have to go with whatever this is. So whenever this changed color permanently, you're going to calculate the volume that you added using the burette readings we just saw, multiply times the molarity, which you will know because it's a standardized solution, and that give you the moles of the substance. That moles is equal to the moles that's in here. They're equal to each other. So because they're equal to each other, what we could do at that point is divide that mole number by the volume that was originally in this container before I added the base or acid, whatever I'm adding, and that gives me the concentration. So that's how you determine the concentration of an unknown, is by doing that calculation. But remember, whatever you come up with is going to be bigger than what it should be. And the reason for that is that you're going to overshoot the equivalence point. And the reason for that is because indicators work in a very narrow range, and it's extremely unlikely that the range that the color change occurred is the exact same number that the equivalence point was reached. So just be aware of that. That's a common issue with this particular type of experiment. Indicators, so you can just be aware that there's a whole bunch of options to do experiments with. All right, titration curve. This is a graphical way of showing titration. Now, if you're doing a pH meter, especially one with like a vernier, which gives you a graphical interface and shows you the graph as you're calculating pH or determining pH, they'll give you a titration curve. They'll build one for you as you do the experiment, which is really cool. What this thing basically does, it gives you a whole bunch of data. pH is on the y-axis. Volume of the acid or base you're adding is on the x-axis. Whatever you're adding is on that axis. And can be used to determine the equivalence point, the K or KB, an appropriate indicator for titration. So it gives you a whole lot of data that you could use. So let's look at a titration curve. First off, this is a strong acid one. The way you can tell it's a strong acid versus a weak acid is the starting pH. If the pH is 1, it's a strong acid. If the pH is above 2, it's a weak acid. So these are two different titration curves. One for strong, one for weak, just so you could be aware of it. The strong acid does not have a buffer region because it's not a buffer. A strong acid can never be a buffer. A strong base can never be a buffer. You need a weak acid or a weak base. So this top one has a buffer region. This is the region that the buffer is effective. Remember, that's that plus or minus 1 of whatever the pK is. So for this, that means that's between 3.89 and 5.89. The reason I figured this out, because the pK is 4.89. Remember, plus or minus 1 of that. So a couple things you need to be aware of it. First off, your equivalence point, the volume for it is right here. So to get my moles of the base I'm adding, because you're adding a base to the acid, you just have to multiply 40 times the concentration of this. That gives me my moles of base that I'm adding. That's going to be equal to the moles of acid in the solution, and I could get the concentration that way. So you figure out if you had a graph, all you have to do is take the volume where they're going vertical, multiply times the molarity you started with, and that'll give you a moles number that you're going to be working with. The other thing to note about this, halfway from this volume, whatever this is, right here, that's your half equivalence point. At that point, your concentration of your weak acid and its conjugate is equal. It's a 1-to-1 ratio. That's important because that's where your buffer is the most effective. That's also where your pK is equal to your pH, right? At this particular point, you are equal. Before this point, your HPR, we'll call it HA, it's HPR here, but we'll just do generic. Your weak acid is going to have a higher concentration until you get to this point. Once you get at this point, these are going to be equal to each other. The HA and the A minus are equal to each other. So what's going to be higher concentration-wise beyond this point? A minus, because you've consumed a enough HA to make A minus, then now the A minus is going to be larger in quantity. Remember, as you're adding base, what's going on? The HA is fighting it. You're adding OH minus, it's going to fight it to produce H2O and A minus. So each time you do that, the concentration of HA goes down. Simultaneously, the concentration of A minus goes up. That's why at this point they're equal to each other. Before here, remember, it was just, here it's just HA purely, right? At this point, now they're equal to each other. And then beyond that, you're producing more A minus. So A minus is going to be higher. And then right here, your HA plus OH is going to equal to 0. They're equal to each other. So basically, they cancel each other's amounts out. Numerically, this is also the point you get the moles of the unknown chemical. But just realize at this point, the HA and OH minus are the 1-1 ratio. So they basically consume each other. So there is no HA or OH minus here for the actual experiment. At that point, both of these are being consumed because they're 1-1 ratio. They're eating each other up. There's nothing of either one, right? Beyond this point, OH minus is going to start increasing in concentration to be higher. So from this point on, A minus and OH minus are going to be highest in concentration as you go. They'll ask you questions about it. That's why I'm pointing all this out to you. So you recognize that, initially what's going to be high, where they're going to be equal, and then what gets higher as you go to the right. The other thing to note is your equivalence point, which in this situation is 8.8. Because you're adding a strong base to a weak acid, you expect your pH to be above 7, right? And that's exactly what it is in this situation. If your base is stronger, your pH is going to be above 7. If your acid is stronger, your pH is going to be below 7. If the acid and base are equal in strength, then it's going to be exactly 7. Those are your options. And you can see phenolphthalein is what's doing the color change. But look at the equivalence point. It's right there. You have to be really, really effective to catch it. More than likely, you're going to probably overshooting it to the pink range, so you'll be overshooting it by mistake. That's all the data you can gather from this. Oh, the other thing, besides the fact that you get the weak acid and strong acid part, you could also figure out the strong base because your ending pH is going to be it's going to be greater than 11. That's the other thing you want to note. Your pH, when it starts leveling off, it's going to be above 11. So for weak acid is never strong, pH is a good pKa. The half equivalence point, which is located exactly half the volume of the equivalence point. Very important to remember that. Because the other thing I want to point out about this, if I could get my pKa, I could get my Ka. If I get my Ka, I could identify the acid. Because every acid has a unique Ka value. So that's the other thing you could do with this. If you're trying to figure out an unknown acid, you could do it through the Ka value. End point is where the color change occurs. All right, effective acids and bases on equivalence point. If the strong acid, strong base, what I just mentioned a second ago, they're 7. If you have strong acid, weak base, less than 7. Weak acid, strong. Basically, whatever is stronger, that's where your pH is going to favor. Acid stronger below 7. Base is stronger above 7. And if they're equal, like in weak base, weak acid, strong base, they're equal to 7. All right, here's another titration curve. Now, without even looking at the data, you should be able to figure out it's a strong acid because you're starting at 1. It's a strong base because you're heading beyond 11. These are all data points you can get real quick. Your pH is exactly 7. Why? Because that's strong acid, strong base, so it's going to be at 7. You don't have a half equivalence point for this because it's not a weak acid or weak base. You can't have it unless they are. All right, let's take a look at another one. Starting at 3, so we know it's a weak acid. Ending above 11, so we know it's a strong base. So we expect our pH, based on the fact this is stronger than this, to be above 7. It is, right? We do have a buffer region. How do you know where the half equivalence point is? Once again, 50, half of it, 25. Here's my half equivalence point. That's going to be my pKa. So that'll give me my range. I can get my Ka as well from there. Now, if I was trying to figure out the concentration of this unknown chemical, just multiply 50 milliliters, so 0.050 liters, times the molarity of what I'm adding, which is NaOH, 0.100 molar. That'll give me my moles. That's equal to the moles of this unknown acid. Divide by the original volume, which is 50 milliliters. Let's just do the numbers real quick. So 0.05. So it's very unlikely they're going to give you this kind of graphical data, but it's never, something you can completely eliminate. So this is going to be equal to 0.05 moles. So remember, that's your moles of your base you're adding, but that's also equal to the moles of the acid you have. So my concentration of this acid, which is acetic acid, it's called HA, is equal to 0.05 moles. Divide by the original volume, which is 0.050 liters. That's what was originally a beaker before you added anything. And you get basically 0.100 molar as well. Coincidence. So this is all the information you can gather real quickly from the titration curves. Okay, so now you have two different ones. You can see the top one's a strong base, the bottom one's a weak base. It's because where the starting points are. You can see you're adding a strong acid because your pH ends around 2, which is what you expect. Equivalence points below 7. Half equivalence point for the blue line is going to be half 50, 25. It's right around there. So your pK is around 9. Let's try some scenarios. Just the graphical information that they give you. So you plot your points accordingly based off of that. So you have A, B, C, D, E, and here are your 4 different chemicals. We ignored the Na plus earlier, but let's go back to it. Okay, so at A, what's the highest concentration? HA, right? Your equivalence point looks like to be around 14. So your half equivalence points can be right around here, around 7. So at this point, we expect our HA and our A minus to be equal to each other. What about Na plus, you ask? Well, you're adding Na plus from the NaOH, right? So initially it's going to be very small. It's going to be one of the lower ones. But once you get to around this point, Na plus starts getting high. It's hard to tell what the exact concentration of Na plus is versus A minus. It's not that simple to just sit there. They should be equal to each other theoretically because you're producing them as you're adding Na plus, and as you're as you're adding NaOH, you're producing an A plus and the A minus. So you can distinguish which one of these are the highest, but they're both there. And you also A minus is going to be higher at this point. So HA is high in the beginning. They're equal at the half equivalence point. Then A minus starts winning, and A plus is a variable as well. And then past this point, when you start leveling off, OH minus starts increasing. It's hard, once again, to tell if OH minus is going to be higher than these two, because it depends on how much you added at that point. You can mathematically verify it, but you're not going to go that far with it. The most you're going to probably do is generality is this, be able to figure out what's going on here concentration-wise. So if you can make those inferences as far as what's highest at those points, you're fine. So at A, HA is greater than A minus, which is greater than A plus, greater than OH minus. At B, they're equal. You expect Na plus to be higher than OH minus. The reason is because you're consuming OH minus as you're adding it, so it's all 0. Up until this point, your OH is losing. It's always going to be zeroed out, right? Whatever you add, it's going to get eaten up. But at this point, when it's starting to spike, that means OH is winning. So at C, A minus is going to be greater than HA, which is greater than Na plus. Na plus HA could be similar. You don't want to make that distinction, but for this one we did. And it's greater than OH minus still, because remember your OH is being consumed. At D, Na plus is starting to win. These two really should be equal instead of greater than. That makes more sense. Which is greater than HA, which is equal to OH minus. Because at this point, remember, they're equal to each other. So they consume each other. And at E, Na plus, well, that would be greater than OH. Because remember, you're adding Na the whole time. You're not producing any more A minus. After this point, A minus is no longer being produced. Because the only way you produce A minus is if it reacts with OH. If OH reacts with HA, right? At this point, you've stopped producing you don't have any more HA to produce A minus. So it levels off, and that's why Na starts winning at point E, then OH minus, then A minus, and then HA. All right, so assume the concentration of NaOH is 0.1 molar, and that you are using 14 milliliters of unknown acid. What is the pH of the equivalence point? 9.35. All you have to do is just go here, go across, somewhere around here, to get the value. You get an exact number, but for this one, just a graphical interface and figure it out through there. Because they're not going to ask you for the math for this part, for the pH of the equivalence point. As long as you say it's above 7, you're fine. I mean, that's as far as you're willing to go with it. What is the Ka of the acid? Well, Ka is going to be point B, and we established that that's going to be at 7, which is around here. It's around 4.8. Not exactly 5, but close to it. If you put 5, you'll be fine too. You're close enough. So your K is equal to 10 to the negative of that, which means your K is equal to 1.58 times negative 4. So that's what you would use to identify the acid if you had to do that. You look at the Ka values and match it up. Closest one to it would be the answer. What's the concentration of the unknown acid? So we take our concentration of the base we're adding times the volume at the equivalence point, which is 14 milliliters, right? You get 0.0014 moles. You know your moles of NaOH equals your moles of HA because it's the equivalence point. So you have 0.014 moles, 0.0014 moles of HA. Divide that by the volume you started with, which is 0.014 liters, excuse me. They gave that to you in the beginning. And that's your answer. All right, in water, hydrozoic acid is a weak acid that has an equilibrium constant equal to 2.8 negative 5. A 3-liter sample, 0.5 molar of the acid is prepared. Okay, so you notice you only have one concentration so far. So it looks like a type 1 question at this point. It doesn't look like it's a buffer question yet. So first you're going to do is write the expressions, so just prox over reactants. We're going to write the reaction out, just dissociate it. You could also just write HN3 plus H2O produces H3O plus N3 minus. Either one's fine. So here's your expression. That's all you have to do for that. For B, calculate the pH of the solution. So in order to the pH, we need to have the concentrations, and we need to have initial concentration. We need to have the Ka. We have a Ka, thankfully, and we have 0.3 milliliter sample. The 0.5 molar solution of the acid is prepared. So we have quantities we can work with. So first thing we're going to do is 0.05 molar. And for those wondering where you get 0.05 molar, right there. So what's the point of all this? Just to mess with you. It's a 0.05 molar solution. So if I take 0.3 liters of it, concentration should still be 0.05 molar. Now, if I was trying to get the moles of it, I multiply, that'll be a different number. Because if I start with 1 liter, that's going to give me a different number than if I multiply by 0.3 liters. So the moles of acid that you're taking is going to be smaller, but that's irrelevant for our equilibrium calculations, because equilibrium calculations are dependent on concentration. So the concentration will still be 0.05. That's where it came from. Notice I have zeros for the other ones because they didn't give me numbers. So it looks like a type 1 possible. 5 times 10 to the negative 2 versus 1.8 times negative 5 looks like it's a 3 or more part. But let's just see if we could do a perfect square first, if that's an option. So we're going to plug in our numbers. It's not a perfect square, so we're going to assume x is small. Solve for x. So you get 0.0018 molar of H plus. That's your H3O concentration. That's your pH. So answer is at 2.93. So type 1 question with the assumption for equilibrium. All right, to 0.15 liters of the solution, 0.8 grams of sodium azide is added. Okay, so the concentration you're starting with is still going to be the same, but now you have a common ion question, right? You have NaN3, which is a common ion. So what do you do mathematically? Well, now you need to account for that. So I'm going to get my moles of the sodium azide, get 0.012 moles divided by the volume to get a molarity. 0.082. So now I have 2 molarities to plug into my ICEA box. So you could see I have a value for this, and I have a value for this is still 0, right? Because they didn't give me anything for it. I'm going to assume it's 0. Plus x minus x. So I already know it's probably going to be an assumption question because quadratic is usually the question for these things. To assume as x is small, we're going to use answer and Hasselbalch. So you have two choices at this point. You could try to solve for x the old-fashioned way, and then get your pH, and then get your H3O and get your pH through there, or you could use Henderson-Hasselbalch. I'm going to do Henderson-Hasselbalch for this because it's a little bit easier. So negative log products of reactants. So I'm going to assume x is small for both of them, so they both go away. That's why there's no x's here. I just do log of products over reactants. And because your top number is bigger than your small number, your bottom number, you could assume that you're going to be adding. So your pH is going to be higher than usual. So you add whatever this is plus this, and you get your new pH, which is 4.76. You could have also done this just solving for x and then plugging in for the log formula into that. To the remaining 1.5 liter of the original solution, 0.075 liters of 0.1 molar of NaOH is added. Now you're dealing with a neutralization scenario. Now it becomes more challenging because you're adding this to the original solution. So now it's a buffer question. So it's a type 2 question. So I'm going to write the reaction for a type 2. Why HA plus OH minus? Because I'm adding a base. So what does the base react with? The acid, the weak acid. So that's where the HA came from. So it produces that. I'm going to get my moles of everything. Now, why am I getting moles of everything? It's a dilution question. That's what makes it nastier. So I'm going to multiply the molarity times the volume for each one. Get it for OH. Now I have moles for both of them. Yay, they're equal, which makes this question even tougher. Because now you have to do a second reaction. I'm going to show you what that looks like in a second. So here's my numbers. For buffer questions, you subtract whatever is the smaller number. So minus 0.0075, you subtract it. They're the same number, but let's say this was smaller than this. You would subtract this from everything on the reactant side and add it to the product side. So unlike what you typically do, where you have minus x plus x, for buffer question, you don't do that. You subtract whatever the smallest quantity is from the reactant side and add it to the product side. So in this situation, they're identical. So subtract from the reactant side, add to the product side. I get that. I'm going to change that to molarity because right now I can't figure out the pH because I don't have hydroxide and I don't have hydronium. So I'm going to do is write a second reaction. So whenever these two are zeroed out, you have to write a second reaction, which makes this really much more entertaining than it should be. Notice once again, now we're going to type 1 question. So after you do your buffer part, which is a type 2, you go back and do a type 1 where you do A minus, which is basically just this. Which is going to be this, and then plug and chug the numbers afterwards. So there's my 0.033. I don't have these numbers because they're zeroed. That's always going to be the case, but when you do a second reaction, your products are always going to be zeros. Minus x plus x, do all this. Now here's the problem. This was originally a Ka question, right? But right now I have hydroxide. Hydroxide is consistent with a Kb question. So you have to be aware of that. That means you have to solve for the Kb. So first you figure out there's a dilution question. You have to calculate the moles, then go to a new molarity. Then you have to write a reaction out. And then you figure out the concentration of that new A minus. And now we need to solve for the Kb, which comes out to be 3.57 times negative 10. And now I'm going to plug in my numbers. So this came from the fact that you have OH minus HA over A minus is equal to Kb. So all I do is just plug in the numbers. These are x plus, that's where this came from, 0.03 minus x. We can assume x is small. You guys can all see that, right? Because this and this are more than 3 digits apart. So our X is equal to 3.43 times negative 6. So now I have an OH, and now I can figure out the POH and then figure out the pH, and that's what I'm going to do. So my POH would be, I think they only asked for hydroxide, right? But let's say you had to do the POH. So POH is equal to negative log of 3.43 times 10 to the negative 6. So when you plug this into your computer, log 3.43 second e negative 6, you get 5.46. So your pH is equal to 14 minus 5.46. So my ultimate pH for this, if they're asking for that, would be 8.54. They only ask for hydroxide. You don't have to go that far, but just in case you had to, that's how you would do it. So that was S&M base, the basics of it. As you can see, there's a lot of math, a lot of thinking, but if you narrow down your options as far as the number of formulas and what type of options you have, it's not as bad. So it just really depends on how you look at them. That's it. All right, titration. Titration is when you're trying to neutralize a substance, and it's primarily used to determine the concentration of an unknown chemical. So there's spectrophotometry, which you use for colored solutions to determine the concentration. Use titration